Hello, my name is Michael Delaney, and today we're going to be doing the BDAN 310 final project capstone. In this, we're looking at two different data frames, the body fat data frame and the my heart data frame. And we're going to be using some created scripts that I created in order to determine or predict the body fat likely or the body fat percentages or the likelihood of heart disease. So looking at the body fat one first, we have some different packages that you install in order to get access to all the functionality needed for the functions in here. This first one is going to be looking for missing values within the data set. We can see at the bottom that there are 0. We're going to use our training data as well as our evaluation data, and this is going to take like an excerpt of the total data set to train off of and then use everything except those data points or the observations in the training data in order to evaluate how accurate your model is. Looking at the tree model here, we're using R part, which is a function. Body frame, or excuse me, body fat is going to be our independent variable based on everything else, which is what the period stands for. Data frame, again, using the training data within an ANOVA method because we are not using a class where it's like a yes or a no. There's multiple different things it could be. Validation predictions, again, it's based on the model we just created using the evaluation data. And then by printing both of these, we can see that the first observation, it predicts that that person will have a 7.66 body fat percentage, but in actuality, they have a 3.7. But if we look at the second and third, we have predictions at 7.7 and 21 and a 7.9 and 23. So it's relative. And then if we look at the actual accuracy of the model, we can see that it has an MAE, or mean absolute error, which is essentially the expected deviation off of the actual point that you can expect. So if it is 1.45, which it is in this case, then you can expect that it'll be on average around 1.45% away from the actual expected value. Now, if we were to look at the linear regression model that I've created, we're going to plot these points, as you can see on the right hand side, with a weight and body fat relation. We're going to create a line to demonstrate the linear regression or the trend of where the body fat is going. And we could even use a predict function and put in a custom weight to see. So at 160 pounds, which would be like in this area, what would their body fat percentage be? If we're going off the coefficient here, it would be about middle of the road between 10 and 20, which tracks because it's about 15.7. And if we compare the two models, we can see that with the MAE being 1.45 and the summary of the other model, we can see that this one is dealing more so along with the standard error of 2.6. So in this case, the tree model is actually a better model for the body fat prediction. Now, in the heart disease one, we are also using a tree model, but we're going to use a logistic regression for the second one. So again, checking if we're missing any data, we are not. So then, just like the other one, we're going to create a or define training data to and evaluation data to. We're also going to create a tree model. And then we are also going to have validation predictions. This does use a class method and type instead of ANOVA and vector. And the reason for that is because we're dealing with a 1 or a 0. So that just helps that remain as a factor. Again, we can print both of these and we can look that it's going to predict that the first one is that there is heart disease and the next two are 0. We can see here that the model does seem to do that. So we'll see how accurate it actually is. And we can print a basic table. And again, diagonals are going to mean the correct prediction versus like the accurate one. So 243 predictions ended up being correct that there is no heart disease. 401 ended up being correct that there is heart disease. But we can see that there are quite a few false positives and false negatives. And we can tell that by running a confusion matrix. And we can look at the accuracy of the model. So around 82%, which isn't bad at all. But we can see that it has a very high specificity, but its sensitivity is low. And specificity is essentially how likely are we to have an accurate prediction of there not being heart disease, and sensitivity is how accurate is the model to predicting heart disease being there. So very useful for specificity. The sensitivity is not quite where we'd like it, but now we can look at a logistical regression. So we're going to create a logistical model here with the generalized logistic function using heart disease as our independent variable. It's going to use everything else in the data set. Binomial. Then we're going to create the logistic model to make predictions about the evaluation data. So we're going to create our S-curve here with the prediction, and then we're also going to do our prediction binary. And this is an if-else statement. So it's essentially saying if this defined variable that we created is greater than 0.5, then yes, then no. we can look at our table and our confusion matrix for this one, and we can see here that there are quite a few more incorrect um, predictions compared to the first model, and this is demonstrated by the accuracy being different at 75% rather than, I believe it was in the 80s, yeah, 82%. And we can also see here that the sensitivity is relative. As a matter of fact, the sensitivity is actually even better, but the specificity is significantly worse. So when comparing these two models, we can see that the tree model had a higher accuracy with a very high success rate and specificity, but struggles with sensitivity. And the logistical regression did really, really well with the, well, I shouldn't say really, really. It didn't do much better. It did better. It did better in sensitivity, but it didn't do quite as well in specificity. But in this case, the decision tree model does fit the heart decision prediction far better. So with that being said, thank you so much for watching this video. I hope that it has made complete sense, and this was a joy to work on. So thank you very much.